We have previously talked about the bad old days of parallel programming, when anything went and people used to write arbitrary multiple threads or processes all running simultaneously and potentially getting into threshold messes. When you have arbitrary programs running at the same time, you run into these classic problems based around race conditions. Race condition means you don't know exactly what order your programs are going to run. So you can have two programs trying to hit on the same piece of data, and that is going to result in non-determinism. That means nobody knows what your program is going to do. It's very difficult to debug, basically impossible to debug. Makes it very difficult to normally verify. More advanced form of making programs work rather than debugging the program work. Just like debugging, that becomes really hard. And we also have these classes of problems when processes have to wait on each other. These bottlenecks, if everyone waiting to access a resource. Or worse than that, they include deadlock, where you have a bunch of programs all waiting on each other and the whole system is that was the bad old days of parallel and concurrent. We've then seen the rise of parallel design patterns, which have developed over time to create sane versions of some of those situations. As with all design patterns, they are standard software architectures which have been found to be useful and good. And in particular, for the case of parallel design patterns, they have been found to remove most of those problems. As long as you satisfy the requirements. So, for example, when we talked about the difference between scatter and gather, you might remember there's a special case you still have to go and prove something. You have to prove that your program isn't going to hit in the same memory location in order to get the patterns we saw last week were deliberately the easier ones. They're mostly patterns that don't involve any communication between the workers, or apart from that little scatter and gather issue, they don't require any further conditions or proofs. Those patterns tend to be the most useful. Many problems in parallel programming are these embarrassingly parallel programs. Remember, those are the ones that are really easy. You can just run the same job on many different data items simultaneously without any interaction at all. So it turns out many practical examples have that form. Pretty much anything in data science, for example, is going to involve chugging through a massive data set and doing the same thing in each program. However, there are other problems in the world which are inherently interactive. These are problems where you do have to have some communication between processes. We don't want to just leap headfirst into those and go back to the bad old days of anarchy and race conditions and deadlock. We would like to develop additional design patterns which have some element of communication between the tasks. But we're going to keep that element carefully under control. We're going to identify what it is, we're going to understand it, and when it appears, it's going to be part of one of these design patterns that has been well developed and tested and ideally proven to avoid both of those kinds of problems. So, kind of with great power comes great responsibility, right? When you're given access to more powerful styles of programming, you can do more, but there are more things that can go wrong. So today we will talk about communication and interaction between programs to set us up for next week when we look at some more advanced design patterns that we can make use of these communication. So the underlying theory of all this is independent of the programming language or system. So in this module we're doing a practical work. just OpenCL. Okay, Chronos defines a particular view of parallel computation with many different languages potentially could use. So OpenCL is just one of a family of Chronos languages. So we will take a look at how Chronos memory works, in particular how Chronos shared memory works, because it's shared memory that we can get our jobs to communicate with one another by reading and writing to the same accessible memory. So we'll look at Chronos shared memory. We'll talk about synchronization. Synchronization means making sure that two programs reach the same point. You might have two programs that are running at different speeds and different orders, but there's a point where you need them to both be on the same line, or at least to know which line each one is on. So that's called synchronization. That's the technical barriers that we do that. We'll talk about atomics, which are a way of resolving multiple people hitting on the same data items. And then we'll look at some examples in OpenCL which are quite closely related to the assessment for the module. So I'll give you some practical CL tips. And through that we'll see how all these ideas can be applied. In this case we'll look at applying reduced. So be careful with this stuff. Ideally, see if your task is embarrassingly parallel, like most parallel tasks end up being, and you don't need anything. If you don't need the for certain classes of problems, whatever, you can tell it as apparently interactive. So in theory, when you bring into process communication, you have unleashed all the power and all the dangers of classical parallel recurrent programming, such as race conditions and bottlenecks and deadlocks. In a language like OpenCL, which we're using in our workshops in the module, CL is it's designed around a particular form of parallelism. If we taught the module in another language, like Go, for example, or Silk, those languages are much more oriented towards that task-based parallelism, where CL has at least evolved from a data parallel. It's evolved from embarrassingly parallel problems like drawing pixels on a screen in a video game, which is where GPUs originally came from. It's come from that kind of SIMD view of the world. Modern GPUs and modern OpenCL are not SIMD anymore. They're really this SPUMD, single program multiple data. That means you have one program, but it's not running perfectly synchronized. And potentially you can get all the power of classical parallelism and concurrency. It's possible to write SPUMD programs which look just like old-fashioned arbitrary parallel code. CL's not really performance on the GPU where the executions are as closely related as possible. Ideally running in SID style will still run much faster. So in theory you can return to the bad old days of complete arbitrary fast parallelism. Both the language itself and this style of programming that I'm teaching you are encouraging you not to do that and to try and stay within these well-behaved design patterns. So, in order to have multiple tasks, work items in OpenCL speak, remember Chronos is the organization that defines these terms. Okay? You might notice I stumble over words now and again. I'm trying to be very careful to use the official politically correct Chronos view of the world. Okay? That's not the view of the world that is taken by some of the GPU manufacturers. So if you see me fumble a couple of words, it's because I'm really trying to hit on the right names. So in Chronos speak, a work item is one execution of your kernel. So it's running on a processing element as part of a compute. So in the Chronos view of the world, you have a memory hierarchy. Think back, if you came to first year computer architecture, which I know you didn't if you're a game student, if you came to first year architecture, you will remember the idea of the memory pyramid. And when we talked about the memory pyramid back then, it was mostly in the context of CPUs. In CPU world, memory really is a pyramid. There's a big memory outside that is slow, and then there are caches that are smaller and faster, and it goes all the way up to the registers in the CPU, which is the tip of the pyramid, which is very small and very fast. When you go to parallel devices, the pyramid is more of a block. You can see this pyramid doesn't have a thin tip and a fat bottom. It's just as wide as it is on top as the bottom. And that's because as you go up this pyramid, there are more and more units of computation. So if we were in CPU world, there'd just be one of these, and you could see a triangle pyramid shape. But in a parallel machine, as you go up the hierarchy, the memory items get smaller, but now there are more of them because they're all running. So according to Kronos, the memory hierarchy looks like this. You have a host, which has host memory. That's usually the RAM of the PC that you're running on. This box is your device, which is usually what you refer to as a GPU. It's the physical thing that you put inside your PC. On the device is what is called global memory. Part of it is called constant memory. It's another form of global memory. So this memory is accessible to everyone on the GPU. We then divide the device up into these compute units. And roughly a compute unit is a place that is going to run lots of copies of the same kernel together. Each compute unit is going to run code called a workgroup, and it's going to have its own local memory. So local memory means isolated within a compute unit, and therefore accessible to all the jobs in a Kronos work group. And then each job, well, we're not allowed to call them jobs, we have to call them work items in Kronos speak. Each work item in the work group then has its own private memory. And that private memory is roughly what a CPU would have internally. That's roughly like the registers inside a CPU. So if you remember all that stuff from first year computer architecture about layers of cache, yeah? In a CPU style architecture, you have the fast registers, you have layers of cache, you have a big memory at the bottom. And from a programming perspective, caches present lots of new opportunities, but also lots of threats. Okay, they present opportunities to make your code go faster by keeping stuff in higher and higher levels of cache, but they present threats because if you do something wrong, if a cache gets out of sync with everything else, then you can end up in a mess. And in a parallel system, this gets more complicated because different processing elements may be requiring to communicate by sharing a piece of memory, and now you've got to think about which level of cache is that data actually sitting at. These numbers give some idea of the sizes on a typical GPU. So you'll probably find this private memory is a few bytes. Okay, this is like the registers. You'll find kilo kibi to mebi bytes. All that binary notation sitting in local memory. And when you get to global memory, this is usually what you see quoted when you buy a 24 gigabyte CPU, for example. That's how much you can sit in here. That number has become very important recently for people training and using large language models. You have a model with 7 billion parameters. You're probably going to need about 12 gigabytes of GPU to run one of those, depending on how it's been quantified. So this has become a very important one. So as a programmer, you can make your code go faster if you understand the memory hierarchy, as you can with CPU. If you move data up the hierarchy, your code is going to go faster, but it's going to be harder for processing elements to communicate with one another. Okay? If you have 4 processing elements and they're all hitting on the same item in global memory, they can communicate really easily by reading. going to go slow because the data is right down the hierarchy. If you move the data up into these caches, the program will go faster, but when they need to communicate, you're going to have to think more carefully about how to update all the caches to get the information shared between them. So a basic parallel programming technique is to move memory up the hierarchy. There are commands in OpenCL, for example, that will let you do that. They'll let you copy information from the host to the device, and then from the device to local, and then automatically it gets moved into the registers. There are programming techniques to make that motion go more efficiently. If you make lots of small loops, if you're constantly hitting on global memory and saying, go and copy this item into local memory, and do something and then send it back, that's going to be really slow, and that's going to be even slower than just working directly on the global memory. So usually what you want to do, if you're going to do this caching optimization, you're going to try and pull everything out of global memory that you think you need. You're going to try and do it all in one big move. You're going to move everything out of global memory into local memory, and that's called privatization. You try and do it in one big move, so you only take one. There's more advanced techniques like coalescence. Coalescence takes advantage of caching between work items. If you have many of these work items running in parallel, they all need to pull something out of global memory. It's usually faster if they all do it simultaneously. If you can synchronize them, now they're all going to read one element of a big array here into their own local memories, but you try and get them to do it all at once, and that's called coalescence. Privatization is a single work item pulling out all its data together. Coalescence is many work items synchronizing their global memory. So here's an example. You remember the stencil pattern we saw last week? Yeah? So stencil is this kind of pattern. You've got a single work item. It is accessing multiple data items. And the stencil pattern means that every work item is sharing data with its neighbors. Yeah? So this data item, for example, is being used by 3 different work items. Yeah? And this pattern is used for any kind of filtering. We talked about image blurring or audio effects. You could make a reverberation effect using this type of pattern. Now, let's look at this from the point of view of the memory hierarchy. Here's a naive implementation of the stencil. So this is an averaging filter. Okay, let's say we're writing this task here, this work item here. This work item is going to hit on 3 data items from neighboring IDs. Yeah, so this is my ID, and these are neighboring IDs. It's going to access them all from global memory, which is slow, do the averaging, and go write the result out there. Now you notice each data item now has to be accessed 3 times, because there's going to be 3 of these work items. All of these 3 work items are all going to hit on that data point. So that's 3 global memory accesses. So we can make this program go faster by using privatization. Privatization means pull in all the data that you need right away. So here's a new version of our averaging filter. In this case, we're going to go grab one item that we need, but we also know that our neighbors are going to be making use of this item. Okay, so look, I'm sitting here, I'm this work item. Before I do my averaging, I'm going to do the work of copying one data item into local memory. Okay? So I'm only making one global memory access when I do that. I'm going to rely on my neighbors doing the same thing. Each of my neighbors has made one global access. And now all the work items in this work group can now see this local memory. Okay? Remember, local memory is shared across a work group. It's shared across all the work items in a work group. And so once we've done the work of privatizing that data, we can then do the stencil pattern. item is then going to hit on these IDs. So I'm using LID for local ID. That means an ID in local memory. It should all go faster. Now there's a problem with this. Can anyone see what the problem is?
Synchronization?
Yeah, the clues in the to-do line. Yeah. This is only going to work if we do this operation after we're sure all these data items have actually been privatized. Yeah? If we make our copy, we know our copy's done, and then go straight ahead to doing the averaging, there's a problem that our neighbours might not have done that. We might end up just reading garbage from. So yeah, here where it says to do, we need to do something extra. We need to wait for our neighbours to finish whatever they're doing, and then we know that it's safe for us to go ahead. And that's called synchronization. Okay. So there are many ways of doing synchronization in CL and in different systems. We'll talk about 3 of them. The point of synchronization usually is that you're waiting for access to some resource, some result stored in a resource. But the result has come from your neighbours. In CL, that typically means a shared memory location. It typically means you're waiting for everyone to do something and write a result into a shared memory location so that it's available for you to use. So some approaches to synchronization, most basically you could run several different kernel launchers. You could launch a bunch of kernels together from the host, wait for them all to complete, and then in the next line of your host code, say go and launch a bunch more kernels. That will guarantee that all the first kernels have finished before you're about to launch the second one. That's slow because you're writing stuff on the host, and anything going between the host and the device is going to go slow. So we'll see this technique with barriers, which is a method provided by OpenCL itself. It allows you to specify that you want all work items to location synchronized before they can proceed. So that's usually what we're going to try and use in OpenCL. We can use a barrier approach. Later on we'll talk about a method called atomics. Any kind of synchronization method is going to impact your performance. Okay? The point of synchronization is you make things wait. Yeah? You've got multiple work items, they're all waiting for each other when they reach that synchronization point. There is inherently going to be waiting around. That's the point of doing synchronization. And we've seen from the bad old days of parallel programming, when people are waiting on each other, that exposes you to bottlenecks and it exposes you to deadlock. So as always, you use this stuff as a last resort. You always try and pick a design pattern that doesn't require any synchronization in the first place. But if you have to, this is the hygienic way to do it. So a barrier looks like this. Let's say we launch a bunch of work items inside a work group. Okay? And remember, each work item could run in a completely arbitrary timing order. You have no idea how CL is going to execute your code. So they're all running the same kernel, but they might all do different things. They might get run in completely random orders. Some of them might wait for others. Share the resources. You have no idea what the hardware is going to do with your code. But if you put a barrier in your code at a particular line, it means every job is going to wait for every other, and when they all reach the barrier, then they're allowed to keep on going. Okay? And potentially you could launch multiple work groups at the same time. You might have a device with many compute units. You might have launched 4 work groups. Within each work group, you're allowed to place a barrier. CL does not provide any ways internally to synchronize across work groups. Okay, so a barrier is only going to work inside a single work group. If you need to synchronize across work groups, then it's your own problem. When you see a barrier in code, it just appears like this. You might have seen this in some of the tutorials by now. There's 2 main ways of specifying a barrier. they don't really synchronize on lines of code. Okay, when you think about a barrier, it looks like you're waiting for programs to reach exactly the same line. Turns out that's not the most efficient way to implement barriers, because what you really care about is synchronizing all the memory accesses. You don't actually care if two programs are on slightly different lines, as long as anything they're touching in common has been correctly synchronized. So when you write a barrier, in your head you normally think of it as two programs are now on the same line. But what's actually happening is the nearest memory access has been synchronized. And you can specify the level that you want that doing. You can say, do you want to synchronize just the local memory access, or do you want to synchronize global memory access? And as always, doing things locally tends to go faster. Yeah, local memory is smaller, it's higher up the pyramid, and it's going to go faster. So if you're just working within a group, you can use local, or if you need to work across doing anything with global memory, and you can use the global version of the barrier. Now be careful with these, because you can get into deadlock. Yeah, deadlock is the worst case scenario of parallel programming. Deadlock is total system failure. Nothing is running. The whole program is frozen. And the main way this is going to happen is if you write bad code like this. Okay. So why is this bad code? This barrier is inside an if statement. Okay? It's inside a branch. If you ever put a barrier inside an if statement, you've now created this non-determinism. You might have half your threads are going to do the if, and the other half might not do the if. And if one or more threads doesn't take this branch, all the other threads are going to continue waiting for it forever. Yeah? You've launched 1,000 copies of this. All 1,000 of them have to reach this same line in order to unblock everybody else. If this thread doesn't take the branch, it's never going to reach that line. And that means all the other 1,000 versions of it is going to hang there. You create a deadlock. The basic rule is don't ever put a barrier inside an if. Okay? That's very, very dangerous. Such bad code, you wonder why the CL specification even allows you to do it. Yeah, and that there was probably a lively debate amongst the CL designers. Should we just automatically check for this and return it as an error if someone's trying to do that? Maybe you can come up with an obscure case where it's safe and you really want it. And probably there was someone on that committee making that argument. If somebody wants more power with more responsibility, and other people will want safety and usability. So what you really mean is put the barrier here. This barrier is safe. This barrier is not safe because it's standard. A fence, in Chronos speak, is a related concept to a barrier. Except it only affects a single work item. The concept of a barrier is multiple work items synchronizing themselves. A fence is only ever going to affect one work item at a time. And the idea of a fence is just to make sure all your caches are up to date. If you're worried about data going out that might be seen by other work items or data coming in that you're relying on from other work items, you can use a fence to check that all your caches are fully up to date before the code is allowed to proceed. So this isn't going to lead to deadlock. This isn't involving relying on any other work item waiting for anyone. It's a kind of lower risk strategy if you can express your algorithm with each work item, just making sure that all its data is up to date. Okay, we talked briefly before about transaction type problems. Let's say you're writing a banking application and people are going to log in and they're going to credit and debit each of the accounts. Yeah? And a typical transaction is some money comes out of one account and it goes into the other account. There are classical parallel and concurrent problems that arise when you do that, which will be exploited by baddies, if at all possible, in case of an online banking application. So you might have multiple transactions going on at the same time. So you might have two different trades come in, and both of them would like to add one to your account. So here, in this case, your account starts off with 17. This guy comes in and says, can I add one? That's supposed to take you up to 18. And simultaneously, another request comes in to add one. Now, if you process them in series, you're going to get the right answer. This is going to take you to 18, and then you do the next one that takes you to 19. So one thing that can go wrong here is both threads come in at the same time, and they both start by reading the original value, which is 17. They both say go and add one to that, so they're both going to get the result 18, and they're both going to write to the data store. So regardless of which way around they execute, we're going to end up with the number 18. This is wrong. You've ended up only adding one, rather than adding both of them. When you consider problems of debiting one account and crediting the other account at the same time, even more things can go wrong. You want to ensure that all that stuff is done together. What happens if the system fails just after you've started debiting the first account? You've taken money out of one account, but you've not put it in the other account. The system goes down, you reboot it. That money has now just disappeared. That's very bad. So we would like to ensure that these kinds of transactions can be guaranteed to work. It's actually really hard to do that just in software. It's really, really hard. It's much easier if you have either hardware support or the support of some lower level in your stack. That kind of support that is needed is called atomics. So atomics are usually primitives, like the primitives you get in the CPU, addition, multiplication, and basic operations, usually quite a small set of them, but when they're made atomic, they are given these guarantees that such situations will never happen. So the word atom, we talk about atoms in chemistry, but the word atom in means a single, unsplittable unit. If something is atomic, it means it's going to either happen or it's going to not happen. If it happens, it all happens. The whole unit happens. So if we make this operation atomic, it means two requests might come in at the same time, but they're not allowed to actually be processed in parallel. If it's atomic, one of them has to get done by itself as a unit. When it's finished, the other one is allowed to get done as a unit. And the whole atomic operation is either going to happen or it's going to not happen. It can't half happen. You can't start doing the credit and not finish it. So in CL, the language itself builds in this concept of atomics. How they get implemented is up to whoever is implementing your OpenCL backend. So that could be implemented physically in a piece of hardware. It could be extra digital logic to a GPU, or it could be implemented using some very, very clever software that comes with a whole bunch of formal mathematical proofs to verify the atomicity. Probably on a modern GPU, you're going to get dedicated digital logic hardware to atomics. And if atomics are specified, they are then going to guarantee race-free execution. Okay? It's a promise by the supplier of that atomic interface that those problems never. They come with a cost. So look, in a case like this, you've got two independent jobs coming in. The point of the atomics is that you're only going to work on one at a time. that is effectively now creating a serial computation. Any advantages we had from parallel execution of these trades is going to go away because we're specifically requesting for them to be done in series. If you have 1 million trades all coming in, that could get pretty nasty. Right? You've now created 1 million jobs that have to be done in series, which completely removes the benefit of doing parallel programming in the first place. So there will be a performance penalty from there's also still some risk because atomics don't specify the order things will be executed. They only specify that you're only going to touch one of them at a time. So in this case it's harmless because adding one from this trade, it doesn't matter if you do that before or after adding one from this trade. If you had a request to divide the account by 2, request to add one, that would be wrong. Then it matters, do you do the division first and then the addition, or do you do the addition first and the division? So atomics aren't going to solve those kinds of problems. They're just going to stop the 2 processes from getting mixed up. In other areas of computer science, you'll hear this concept of a transaction. Have we done transactions anywhere? Databases, operating systems? Yeah. The transaction is a higher level concept than the atomic. Transaction is normally quite a complex sequence of operations, such as crediting one account and debiting another account. Atomics aren't going to do that, but they can be used as building blocks to create transactions. So if you've seen transactions in other parts of computer science, this is one way of creating transaction. Atomics are these usually very small basic operations. They're things like adding, subtracting, Boolean stuff, min-max, swapping memory is really important. But very often in parallel programming, you want to just swap 2 data items. When you think about it, that's actually quite hard to get right if people are trying to do it in parallel. You take data out of one place, take data out of another place, store them both somewhere else, and write that data in there, and then write that data in there. That's actually quite a complex sequence of operations. And if 2 people are trying to do swaps at the same time, hitting on the same item, you can get to that. So swap is often a popular candidate for hardware atomic implementation. So you only get a small collection of operations, often only defined on integers. It's your problem to use these atomics to construct anything larger, to build a transaction. And they are going to slow your program down because the whole point of an atomic is that if 2 atomics try and hit on the same piece of data, they get serial. Serialization means some of them are going to be waiting. So as with all communication, use atomics sparingly. Sometimes they are necessary. If you find your code is just full of this, maybe you have bigger things to go and worry about. Ideally, you want to be using them as part of a well-understood design pattern that you control. If you find yourself filling your code with custom atomics, you may be doing something wrong, and you'll maybe bring back to the bad old days of code programming. So, yeah, use them sparingly and preferably as part of a recognized design pattern. These are the set of atomics that you get in Kronos. Kronos includes OpenCL, but it includes all the other languages that meet Kronos classifications as well. So, for example, you'll find one in SQL. SQL is kind of like OpenCL, but you don't have a separate kernel code and a host code. You can write the whole lot in ordinary C++ using the same Kronos methodology. Okay, so let's see some examples of how all these things can put together to make a program go really fast. Okay, and this is the kind of thing we're going to be doing in the assessment. So let's take a basic pattern like reduce, and let's see how we can throw a bunch of OpenCL techniques at it to make it go as fast as possible. Right? So remember the reduce pattern we saw before. And this is an example of reduce. We are together, we'll taking a map of million numbers, many different operations, and go to it. So, an idiot way to implement reduce would be through multiple kernel launches. Okay, so remember, before we got to barriers, we talked about doing synchronization through multiple kernels. We can do each wave of this reduce as a separate kernel. So in this example, I've just shown 2 chords. You need to make several to do this. So look, in this case, we've designed 2 different kernels. This is the kernel for doing this step, this is the kernel for doing this step, and we've given 2 independent launches of those kernels in postcode. Now this acts as a synchronization method. Okay? This line on the host is running a serial program. This line will block until all those kernels have finished. Okay? When they finish, the next line will. This is a kind of idiot synchronization method, just using host code. This is slow because you've got communication going on between the host and the GPU. So an improvement to this would be do everything in one big kernel on the GPU. So what we have here, we've just taken both kernel codes here and we put them inside a single kernel. So we do the first one and then we do the second one. In this example, I've given you 3. Okay, 3 rounds of reduction. You can see each round has a different, this is called the stride length. So like here the stride length is 2, here the stride length is 4, here the stride length is 8. Okay. You come across strides a lot in GPU programming. Whenever you have all your data in an array and you're picking which elements to use, that's a stride. You'll see it a lot in neural network programming, particularly convolutional networks. But we now have a stencil-like problem that we don't want to start the next piece of work until we're sure that all the first piece of work is finished. Right? So to do that, we're going to use barriers. These barriers are replacing the need to do multiple host kernel launches. So in this case, we've said, everyone go do this, everyone do your first slide, but then wait until all my neighbors have finished doing it. When we're confident everyone's done it, then go and do the next round. Okay, wait for that to finish, and we'll do one. Let's make it a bit more efficient. So this is kind of stupid programming because we've written the same function 3 times, basically. This is kind of boilerplate before we start. That's a pattern, if you remember, old-fashioned design pattern. So let's make it a bit more generalized by replacing those 3 separate runs with a loop. Okay, and here we're saying update stride. You see the stride gets twice as big every time. So putting it in a loop now means you can run this on arbitrary data sizes. Okay, this is going to figure out this stride size from the length of the data. Every iteration of the loop comes with a barrier at the end. So you keep going round, you synchronize, change the stride until you're finished. Okay, let's hot rod it some more. So you notice everything here is using global memory. Global memory means memory on the device. It's on the GPU, but it's not the faster local memory that you need to work with. So let's do some local memory privatization. That means copying everything you need out of global memory, bringing it up the memory hierarchy. All that computation in there. So remember, each work item needs to see multiple inputs. But we're not going to have each work item copy all of its inputs. The inputs are shared with other work items. That will be inefficient. So we're going to get each work item to copy one input, the one that has the same ID as itself. We're going to wait for all our neighbors to do the same thing. And that's going to result in all the data that everyone needs to get from memory. So we need a barrier to do that. In this case, it is a local barrier. Right? We're saying wait until everyone has finished hitting on local memory. We're actually making use of local memory in this case. There's the same code we had before. There's the same barrier we had before. When we're done, all the results are in local memory, so we're then going to have to go and copy it back to global memory at the end. Remember in particular the host, that's the main PC outside the GPU. The host can only access global memory. So whatever your result is going to have to go back to global memory so it can get put in the buffer and then sent back to the host for using web keys. Okay, there's a little bug in here, a very, very subtle bug. And this is the kind of place where parallel programming can get very nasty indeed. We can see we're adding things here, and it's possible that two work items might want to hit on the same piece of memory at the same time. So just to take care of that, we're going to put in an atomic. We're going to say if two people want to hit on the same location, take turns at accessing it. What if your data gets really big? We've seen this with some other design patterns. If you're doing large-scale data science, for example, you could have a data set that is bigger than the size of your compute unit, or potentially even bigger than the size of your whole device. So let's take the case of exceeding the size of a compute unit first. That means you're going to have to run multiple work groups, at least. Remember, CL is clever. CL will let you launch as many work groups as you like. If you run out of compute unit capacity, it will automatically serialize. Use the same compute unit multiple times. So this kernel is designed to run as a single work group. If you want to go even faster than that, you might make several independent launches of that work group. Okay? So that's the whole work group getting run multiple times on multiple compute units. So at that point, you'll have to do a little bit of work as a programmer to collate the results together. If you've got different work groups running, they all give you an answer. The reduced pattern is inherently subdividable, so you can take all the answers from different work groups and do the same process that each work group was doing on its own to come up with the final answer. So again, as a programmer, you can decide how you want to do that. One option is to launch a bunch of work groups, get their results, put them all into a new array, and then call the same kernel on that array. Yeah? And potentially that could scale indefinitely. You could do this many, many times to create a hierarchy of reductions. So be careful if you're doing this kind of thing, because there's a difference between the global ID and the local ID. So when you launch a kernel group in OpenCL, every instance of your kernel gets a number that tells you which one it is. Yeah? If I'm the 7th kernel to be launched, probably I'm going to start by looking at the 7th item of memory. That's how I differentiate my behavior from everyone else's behavior. If you've got multiple work groups running in parallel, there's now a difference between the global ID and the local ID. The local ID is your position within a work group. The global ID is your position with the entire set of work going across the work group. So just be aware that you can get a global ID and a local ID, and make sure that you're using the right one. So in some cases, you might not want the overhead of doing another kernel launch. Okay, for problems that are really big, you want this to be recursive. You want to keep doing kernel launches in multiple stages of the loop pattern. For small jobs, you can do it all in a single work group. If you're in this kind of intermediate size, where it's not really worth doing the whole recursion thing and loading a new kernel, for intermediate size problems, you might want to do the last part on the host in the software. You might just want to take the result of all your work launches, and then on CPU code, just do that last round. Okay? That's actually quite a common situation. It just turns out that the sizes of many problems and the sizes of available GPUs often lend themselves to that. It's not worth the overhead of launching just one more kernel to do that if you run on CPU. So sometimes you make the trade-offs. Decide, do I want to do the full recursive GPU thing? Do I want to do the CPU thing? Or can I just fit it all in a single work? So really advanced optimization. So you find with parallel programming, and especially with CL, you can kind of just keep on going and make your program go faster and faster and faster. Some people enjoy this process. There's another optimization we can do. Instead of storing the data in this pattern, we can shift it so that it is sequential. The reason we do that is because of how caches work. Memory access is faster if you hit on things that are contiguous memory. So if you're hitting on data that is spread out, that's going to take longer than if you hit together. To really understand how your cache system works, you can then pick a different memory layout and make the thing go even faster. That requires quite an advanced knowledge of how your particular system actually works. And in particular, CL is often not helpful telling you what that is. The whole point of CL is it's an abstraction. CL was designed by a committee who wishes to prevent individual GPU makers from dominating the market. And so CL is deliberately designed as a higher level abstraction that shields you from some of the detail. But in practice, the particular GPU you run on is going to have different speed properties. So often in a case like this, you'll find CL just randomly gives very different timings of things. If you were to use a lower level view of what the GPU is doing, you'd actually see why. But sometimes you can use that knowledge to make the CL code go faster. Okay, so that's communication. We can make use of this in the more advanced design patterns. The moral is be careful. With great power comes great responsibility.